In part 2 of today's lesson, we're going to be learning about the horizontal line test, how we can check if two functions are inverses of each other, and then lastly, we're going to be looking at an application problem and the importance of your labels. So the horizontal line test is this first thing we've got on the screen. This line test basically is going to help you determine if the inverse of a graph would be considered a function. And remember, a function is something that has one x goes to one y. Okay, so there are no repeating x's. And you could sit here and try to determine all of the points of the inverse and then check for repeating x's, but sometimes having a graph is way faster. So the horizontal line test, what we're going to do is use a horizontal line. You could use your pencil or anything like that, or just visually you could do it. You're going to draw a horizontal line through any part of your graph. And what you hope for is that the graph only hits the line once. Well, in this example of this graph, notice that my horizontal line hits the graph 3 different times. So that means that it fails the vertical or the horizontal line test, which means that the inverse of that graph is not a function. Okay. So this is just to check if the inverse is a function or not. Okay. Same thing I could do with the second graph I have here. So let's draw this horizontal line anywhere through this particular graph. Notice that every time I draw a horizontal line, it only hits the graph in one spot at a time. So that means it passes the horizontal line test, which means if I were to draw this inverse, the inverse is a function. So on a test, if I ask you how or is the inverse a function, why or why not, you would want to use your horizontal line test if you have a graph, and then you could explain because it passes the horizontal line test, or there are going to be no repeating x's in the inverse graph. Okay. Now, if you were given two functions in an equation form, and I'm asking if they're inverses of each other, this is where you're going to have to do it algebraically, and this is where you're going to be using composite functions like you learned about in the last section. Remember, composite functions basically is asking you to use substitution. So to check if two functions are inverses of each other, we're going to plug one equation into the other, and if you do, you should get x. And then we're going to reverse it. We're going to plug the first equation into the second one, and you should also get x. So that's what this rule is right here. So we'll use composite functions, doing f of g of x to get you x, and then getting g of f of x, which would also get you x. And if you don't get both x's, then that means that they're not going to be inverses of each other. So let's try this example here and test to see if they're going to be inverses. So we'll start with the f of g of x. We're going to plug g into f, which is going to get us 3 times 1/3 x minus 3, and then plus 9. So I'm going to go ahead and simplify this, and remember my goal is that we want an x at the end. So distribute the 3, we get x minus 9 plus 9, and the 9's cancel, and we're left with x. So this is a good thing. Okay, so we've done one. Now we need to do the other. So I'm going to do the g of x part now. So remember, we're going to plug f into g. So that would look like this. 1/3 times 3x plus 9, and then minus 3. Again, distributing the 1/3 gets us x plus 3, and then bring down that negative 3. And the 3's will cancel, which will also leave us with an x. So because we've got x's in both equations, this is going to be two inverse functions. So this is going to work. Okay. If you get anything other where they don't match, then automatically you would say no, they are not inverses of each other. The last example we're going to go through, bear with me because I know it's a lot to read, but it's very important. When you're doing application problems, you want to really make sure you're labeling your problem correctly. And the reason for this is because when you start putting units into a problem and you start switching the variables, the relationship between the variables will change. And if you don't change the way you label it, then the equation you get for your inverse will not make sense. Okay, so it's very important. So we're going to go through this example step by step, and I'll show you why it's so important to label. So it says, Larry and Sally are planning a wedding reception. It costs them a base fee of $2,000 plus $50 per guest. If their budget for hall expenses is limited to $10,000, and then I want you to fill in these answers. First, state the cost as a function of number of guests. So we need to know what our variables are first. We'll say that C is the total cost, and then G is the number of guests. So labeling your variables is very important at the very beginning. And now we want to write a function, or in other words, we want to write an equation using these two variables. So we'll start off by saying the cost, which is dependent on the guests, so C of G, is equal to the $50 per guest plus that base fee of $2,000. So this equation represents how much they would have to pay based on the number of guests that they have. All right? So in part B, it says determine the expression for the inverse. Now before, we knew that with the inverse, we switch our variables. So that would mean we'd get G is equal to 50C plus 2,000. And then we would solve back for our original variable. So I would subtract 2,000. And then I would divide by 50. And when you do that, you get that our cost is equal to the guests minus 2,000 divided by 50. But there should be a red flag here. The problem is that we know our cost is dependent on guests, but if you had 100 guests, that means your cost would be negative, and that doesn't make sense to the problem, because obviously the more guests you have, the more money you're going to spend. So because we're doing inverse, we're actually changing the relationship of our variables. If you look at part A, we said the cost was dependent on the guests. So when we find the inverse, that means it's reversed. So now instead of cost being dependent on the guests are dependent on the cost. So instead of C of G, which is what this original was, now it's G of C. So the guests will determine the cost. And so that means that the G that was here really is now going to be our cost. So C minus 2,000 over 50. So basically what I did was just reversed my variables back. Okay, I just changed the notation. So originally it was cost affects the guest. Now it's guests determine the cost. Okay, so I just flip-flopped. And now it makes more sense to our problem, because if I can tell you how much you paid, that's going to determine how many guests you can have. Okay, so there's our part B. And then it says state the domain and range for the situation. So remember, domain is our dependent, or our x's. In this case, that's the guests. And the range would be the cost, or our y values. So we're going to go ahead and figure out how much we can spend. Well, we know that for the number of guests, we can't have less than 0 guests. So we're going to go from 0 to some number. And the thing we have to figure out is how many guests max can we have and be within our budget. Now they said at the beginning the budget was $10,000. So this is where the inverse can come in handy. So if we know that the budget is $10,000, we're going to use our inverse equation, because we know the cost, and determine how many guests we could have with that budget. So I'm going to go ahead and plug that in. So G of C is going to equal $10,000 minus 2,000 divided by 50. And then we're just going to go ahead and simplify. So $10,000 minus $2,000 is $8,000. Divide that by 50, and that gives us 160 guests. So this is why I said the labels on the inverse are very important. Otherwise, you wouldn't know where to plug your number in. So that means we can have a max of 160 guests. And then for the cost range, this one, you don't have to do any calculation, because they tell you your budget is $10,000. So that means that we would have a minimum budget of 0 and a maximum budget of 10,000. And then we're done. So inverse here was very helpful, because we didn't know how many guests we could have within our budget. So we found the inverse, made sure our labels were clear, and then we used our budget to work backwards to find the number of guests we can invite. And that's it. So if you have any questions about the labels, I know it can be a little bit confusing, but remember, inverse is just flipping things around. So you have to flip your labels when you have units in a story problem. If you need more examples of that, please let me know in class and I'll go through those with you. But that's it for today's lesson. Thanks for listening.